Hey, what's up? It's your old pal, Mr. Cook, and we're going to go through these integrals for the part 2 test review for unit 4. So we already had an earlier video going over the different ways to decide what method that you're going to use. And remember that the majority of this test is going to be based on picking the right method for the right integral. Okay, so make sure that you watch that video if there's still some confusion. I'm going to make a video going over like all the different parts here. So this video is going to be going over trig substitutions. I'm sorry if my voice goes out a little bit. I'm a little sick. I'll do my best though. Okay, so the first trig substitution is number 9. So yeah, let's work through it. So first, a little bit of backstory on trig substitution. It's just a way for you to relate x over to theta, and if you're using theta, you can use ratios of sides. You can use all those nice trig properties and trig identities to simplify the expression. That's like kind of the main idea behind it. So when you do a trig sub, there are 3 things to memorize. So it's basically off of different forms. So if I see like a x squared plus a number squared, we'll call it x squared plus a squared. That's a way for me to use a trig sub. I can use it in that case. It's not always going to be ideal to use it, but I can use it when I see an x squared plus an a squared. Same thing with the other ways to go about it. So a squared minus x squared or x squared minus a squared. All those are possible trig substitutions. And when I see x squared plus a squared, what I do is I substitute in, for my x value, whatever this is, okay, I replace it with a, so whatever that number is, a times the tangent of theta. And then I take its derivative, because if I'm working with an integral, I also need to replace the dx in there for a full substitution. So I end up with something like this. And then with a squared minus x squared, that's going to be the case where you've got sine, so it'd be x is equal to a sine theta. And then dx would be equal to cosine of theta d theta. And then the last one is if I see x squared minus a squared, I can replace that x with a times the secant of theta. And the derivative of secant is going to be secant times tangent. Okay, so that's like kind of a like what you should know for each of these. Every time that you recognize that you can do a trig sub, and you pick which trig sub that you're going to use, like tangent, sine, or secant, you should also pair it with a visual understanding of how the x value relates to the theta. And here's how you can do that really easily. First, you decide which substitution you're going to use. Like if I use tangent, then x equals a tangent theta. X over a is going to be, well, let me back up a little bit. If I divide both sides by a on this case, on this substitution, I get x over a is equal to tangent. Remember, tangent is the opposite side over the adjacent side for theta. So that means that x would be the opposite side and a would be the adjacent side for this relationship. And if you use Pythagorean theorem on it, then you get that the square root of x squared plus a squared is going to be your hypotenuse. Similarly with sine, right? Like you can make the sine ratio pretty easily. Remember, sine is opposite over hypotenuse. So if you take this and divide both sides by a, then you get sine is equal to x over a. Remember that sine is opposite over hypotenuse. So that means that the opposite side is x, the hypotenuse is a. And that means that the adjacent side is going to be a squared minus x squared, which is like this pattern right over here. Okay, and then if you, and then the secant one is going to be pretty easy as well. Make your little right triangle. And then if you divide both sides by a over here, you get secant is equal to x over a. Remember, secant is hypotenuse over adjacent. So the hypotenuse is x, the adjacent side is a. That means the opposite side is going to be square root of x squared minus a squared. Okay, so now it's just kind of up to you to figure out which trig substitution you're going to use in which case, and then sort of like you can either direct substitute everything or find the ratio that it represents, and take the antiderivative in either case. So with number 9, I've got x squared plus 16. So that's the x squared plus a squared form. And I can see pretty easily that a is going to be equal to 4 in this case. So I just do my substitution. So x is going to be equal to a, which is 4 times the tangent of theta. And that means that dx is going to be equal to 4 times the secant squared of theta d theta. So I've got 2 routes that I can go, with this. I can do direct substitution, so I'm going to do that. I'll call that like pathway A. And then I could also like be creative and find the ratio that this represents right here. And that sometimes cuts out a lot of steps and is a little easier. But it's harder to use because you gotta be creative about it. So if I wanted to just like mindlessly go through this problem and very procedurally, I would just do this pathway A, direct substitution. So what I do is I make my triangle, right? So if x is equal to 4 tangent theta, if I divide both sides by 4, x over 4 is equal to tangent of theta. And remember that tangent is opposite side over adjacent side. So that means that if I use Pythagorean theorem, my hypotenuse is going to be x squared plus 16. Okay, so the direct substitution route means that I just, wherever I see an x, so with like square root of x squared plus 16 and a dx, I'm going to replace the x with 4 tangent of theta, okay, directly substitute it in. So 4 tangent theta squared, and then that dx even gets replaced. It becomes 4 times the secant squared of theta d theta. So now this is a full substitution. Everything's in terms of theta. So what I would do is I would simplify it. So along with your trig substitutions, you're also going to want to remember, and this is, I think, just really helpful for Calc BC in general, make sure that you know the Pythagorean identities. So sine squared of theta plus cosine squared of theta is equal to 1. Tangent squared of theta plus 1 is equal to secant squared of theta. 1 plus the cotangent squared of theta is equal to cosecant squared of theta. Those 3 you should know. And you can derive them all from sine squared plus cosine squared equals 1, but maybe I'll do that on another video or something. Okay, so here's why it's helpful to know those, because once you do direct substitution, it's all about just simplifying from here. So, I put the 4 secant squared in the numerator. And then if I were to square this out, I would get, let's see here, 16 tangent squared of theta plus 16. Then I'd notice that I have 16s for both of these, so I'd factor those out. So I'd get 4 secant squared of theta over the square root of 16 times tangent squared of theta plus 1. And this is where those identities really help out. Notice that we have tangent squared of theta plus 1, and tangent squared of theta plus 1 is equal to secant squared. So I'm going to replace that with a secant squared. All right, now I would use the square root on this, and here's what I'd end up with. I've got 4 secant squared of theta. The square root of 16 is just 4. The square root of secant squared is just secant. And then, you can simplify it. The 4's divide out. Secant squared over secant just makes a regular old secant. And then this is a really easy antiderivative from here. So this is a memorized one. The antiderivative of secant is natural log, absolute value of secant of theta. Excuse me, plus the tangent of theta. And then plus your constant c. All right, so that's one way to do this up to now. It's just direct substitution. But another way to do it allows you to bypass probably like a couple steps, and then also some thinking that you'd have to do, like a lot of the thinking in terms of using identities and things like that. But you have to be creative in the way that you do this approach. So I'll show it to you, And I'm just going to let you know that this is easy. So if you can like spot how to do it, cool. I'll like show you in each of the different trig sub parts where I'm able to do this. But by no means are you supposed to use this every time, because sometimes it's easier just to do the direct substitution so you don't have to think about it. But B goes like this. Okay, so I start off with my integral 1 over square root of x squared plus 16 dx, and I do a direct substitution for this. But what I'm going to do is I notice that I've got a fraction here, right? And it's a constant value over this side. Now that square root of x squared plus 16 is this side right here. It's the hypotenuse side. So the idea is this. I can actually turn this fraction just directly into a ratio. And it's going to allow me to get that secant of theta d theta that I got over here. It's going to allow me to get it like really quickly. So here's how I do it. So I recognize that I got the hypotenuse in the bottom, and 1 is a constant, just like this number 4. So if this 1 was somehow magically a 4, it would just be the adjacent side over the hypotenuse, cosine. So here's how I do it. I change it into a 4. So I multiply the top by 4, and I immediately also divide by 4. So multiply by a 4th out front. That allows me to create this ratio of the adjacent side over the hypotenuse. So this whole part right here just becomes 1/4, and then all this stuff just becomes cosine of theta, because I was able to create that ratio of adjacent side over the hypotenuse. I still have to get rid of the dx, by the way, so I have to replace that with 4 secant squared. But you can see pretty quickly that this is going to reduce really nicely. Let's see, like the 4 and the 1/4 cancel out. And then secant squared is the same thing as saying 1 over cosine squared. So this becomes, that cosine's there. And then secant is 1 over cosine squared of theta. So now if I make this into one fraction, I've got cosine of theta over cosine squared. Now if I cancel out one of the, or divide out one of the cosines, I just get 1 over cosine, which is, of course, secant. So this becomes secant really quickly. And you end up at the exact same spot, right? But I guess you do like less steps, and it's a little bit easier. Whichever one made more sense to you, stick with that. I'll try to do both for all these problems, but it tends to take a little bit of time when you do that. Okay, so either way, you end up with this antiderivative here. Or sorry, I don't know why I put that. That's similar. It's this antiderivative right here. And so we're not quite done though, because we need to get in terms of x. So the last thing is, when we have our antiderivative, so we've got natural log absolute value of secant of theta plus tangent of theta plus c. Now we've got to turn it back into x. So what we do is we go over to our triangle over here, and we just replace these ratios. So secant is the hypotenuse over the adjacent side. So the hypotenuse on my triangle is the square root of x squared plus 16. The adjacent side of my triangle is 4, so that just becomes x squared plus 16 over 4. And tangent is the opposite side over the adjacent side. So it's going to be x over 4. And then I can just leave it like this. That's my completed antiderivative using trig substitution. Excuse me. Okay, so there's the first trig sub. And, the next ones are going to be pretty fast because, I went through all of the initial steps or inaugural steps and explained where trig subs come from and all that crap. But really, these go by really quickly. There's not even that much. I did a lot of extra writing, I think, that I wouldn't usually do for trig subs. So let me clear this out, and then we'll get started on the next one. So the next trig sub is number 14. And I know that because I've got something squared minus x squared. And, that would be the sine ratio. So I'm going to replace it with sine. So the x part right here, x plus 5, is equal to a times sine theta. So a is going to come from here. That's 3 squared. So my a is 3. So 3 times the sine of theta. And then, I get the derivative from this. So dx is going to be equal to 3 cosine of theta d theta. And I get my little triangle as well. I can make that. So let's see here. If I take x plus 5 and then divide it by, if I divide both sides here by 3, so x plus 5 over 3 is going to be equal to sine. So if this is my angle, my opposite side is x plus 5. My hypotenuse is 3 because that's what the sine ratio is, opposite over hypotenuse. And then the missing side is going to be 9 minus the quantity x plus 5 squared. Okay, so there we go. That's what I needed. I got my triangle. I got my substitutions. And now I can just go ahead and work through the problem. So with direct substitution, let's see what I would end up with. So integral 3 over square root of 9 minus x plus 5 turns into 3 sine theta. So that's going to be 3 sine theta squared. And then times dx, and dx is going to be 3 cosine of theta d theta. So that would be direct substitution. Then you can do all of your identities and stuff. And here's what you'll end up getting. And this is where now I'm going to do the other method. So this is direct substitution, and you can keep going with this, okay? But I like to do the one where I just make the ratio. So I notice that I have the side length 3, which is the hypotenuse. So if I have 3 over square root of 9 minus quantity x minus 5 squared, x plus 5 squared, sorry, dx. 3 is the hypotenuse, so this is hypotenuse. And then square root of 9 minus x plus 5 squared, that's the adjacent side. So this whole thing, this whole big ratio right here, just turns into hypotenuse over adjacent, which is going to be secant. So that whole thing just becomes a secant of theta. And then dx is going to be 3 cosine theta d theta. Okay, and then secant is the same as saying 1 over cosine. And cosine over cosine just cancels out. So all I have is 3. And what's neat about that is that, like, if you did work with this problem over here, like, and do the identities and all that stuff, you would have ended up with exactly what I have right over here, just 3. Okay, so now I do my antiderivative for this, and I just get 3 theta plus c. And then I substitute back in. So I need to get theta all by itself. So I use my substitution over here. And let's see here. If x plus 5 is equal to 3 sine theta, to get theta by itself, I divide by 3. And then to get theta by itself, now I just do the inverse function for sine, arc sine. So that means that theta is going to be equal to arc sine of x plus 5, looks like an A, x plus 5 over 3. All right, so that's the last missing part, 3 times arc sine of x plus 5 over 3 plus c. There we go, that's it. All right, moving on to the next one. Where's the next trig sub? There we go, 17. Okay, so I've got something squared plus some number squared. So x squared plus some number squared. This is going to be tangent. So here's what I would do. I'd let x minus 10 be equal to, let's see, so the a value here would be 6. So 6 tangent of theta. Then if I did the derivative, dx is going to be equal to 6 secant squared of theta d theta. And then I would do my direct substitution if I want to go that route. So here's how it would look. So 2 over, and then let's see here. Instead of x minus 10, I'm going to put 6 tangent of theta squared plus 36. And then dx becomes times 6 secant squared of theta d theta. So that's if you did direct substitution. That's what you do. And then, you'd use your identities and simplify it. So dot, 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 dot. And here's what you'll end up with. So, all right, now I'm going to do the other method of just direct substitution. So I make my little triangle. All right, so tangent is opposite over adjacent, so opposite side is x minus 10, adjacent side is 6. Hypotenuse is going to be x minus 10 squared plus 36. Okay, so what ratio do I get? Well, first off, notice that we don't have a square root, right? So this is the same thing as saying the square root of this squared, right? Because they cancel each other out. So technically what I got is a constant over a square root twice. So I'm going to do that. I'm going to make my constant value 6 over my square root twice. So x minus 10 squared plus 36. And then 6 over square root of x minus 10 squared plus 36. And then if I multiplied 2 6's in there, but I didn't have them initially like in the numerator, I got to divide both of them out here. So I'm going to divide by 6 times 6. But I do have a 2, so I'm also going to multiply by 2 in the top. Okay, so what ratio is this? 6 over the square root of something. So 6 is the adjacent side. Square root of whatever is the hypotenuse. So it's adjacent over hypotenuse. So if this is adjacent over hypotenuse, this is a cosine. So this becomes 1 over 36 times 2. And then, because I moved that 2 up front. And then adjacent over hypotenuse is cosine. So it's going to be cosine of theta. And that's also going to become a cosine of theta. And then dx becomes 6 times the secant squared of theta, d theta. Now remember, so cosine times cosine is cosine squared. And remember that secant squared is 1 over cosine. So this becomes 6 times 1 over cosine squared. And see the cosine squareds cancel out. Leave me just with 6. And then a d theta. And that's what you'd end up with either way. Maybe I'd move the 6 out front also. So let's see, 6 over 12, so that ends up being like a 1/3. That's what you would have ended up with if you like did the direct substitution route and simplified it. It's simplified. You'd just end up with a simple constant value. So anyways, I've got 1/3 and then 1 d theta is antiderivative is theta, so 1/3 theta plus c. So now what I have to do is find out what theta is. So I use my original substitution and get theta all by itself. So x minus 10 is equal to 6 tangent of theta. So to get theta all by itself, I divide by 6 first. And then undo the tangent, so I have arctan. All right, so I get 1/3 theta, which is really arctangent of x minus 10 over 6, and then plus the constant c. All right, there we go. So that's the next trig sub. And then when do I have another trig sub? Oh, I skipped it. Sorry. 32 is the next trig sub. So this is going to be completing the square and then using a trig substitution. So usually, like if you have a quadratic in the denominator, you can use factoring skills to just like use partial fractions. Sorry to get some water. But if you can't factor it, the next thing that you would do is complete the square and then do a trig sub. This is another method that we went over in the notes. I think like pretty early on. So if you can't factor x squared minus 12x plus 32, complete the square on it. So we end up with, let's see here. Completing the square there, we get x minus 6 quantity squared plus 38. And then whenever we, add in that 36 right over here from the negative 6 squared, we got to subtract it as well. So 38 minus 36 is just 2. So there you go. This can be used just as a regular old trig sub now. So if you have something squared plus some other number squared, this is going to be tangent. So what you can do is substitute that x value in, x minus 6, with, let's see, what's the square root of 2? Well, it's just square root of 2. Square root of 2 times tangent of theta. And then if you use the derivative, dx is equal to square root of 2 secant squared of theta d theta. And with direct substitution, here's what you'd end up with. So this becomes 1 over, and then x minus 6 is really square root of 2 tangent theta d theta. Or sorry, tangent of theta, and then squared, then plus 2. And then d theta becomes square root of 2 secant squared of theta d theta. So I guess on the previous problems, I just did the find the ratio thing. So for this one, I'll start with direct substitution because I haven't practiced with this, and I think I only did it in the first problem. And I'll just show you the steps for direct substitution for this one. So if I were to square the square root of 2 tangent of theta, that would become positive 2 tangent theta. And then notice that I've got a 2 here and a 2 here. So I'd factor out the 2 from that. So I'd get 2 times tangent of theta. And then if I divide 2 by 2, I get 1, so plus 1. And remember that tangent squared of theta plus 1 becomes secant squared. So this whole thing just becomes a secant squared. Now if I move that stuff up to the top, let's see, I got a square root of 2, secant squared of theta, and then d theta. The secant squares will go away. Leave me just with square root of 2 over 2, d theta. Now if I take the antiderivative of this, I get square root of 2 over 2 theta plus c. But now I've got to solve for theta, and that's when I use my substitution over here. So if I do that, I get tangent by itself. I divide both sides by square root of 2. And then I take the arctangent of both sides to get theta by itself. So it's arctan of x minus 6 over the square root of 2. Okay, so that's what theta is. So I just finish writing it up. And then plus c, my constant. All right, that's all the trig sub problems on this worksheet. Yeah, so just watch the videos that you need. If you need help, I'm sure that your teacher will be there in the morning before test day to help out. All right, thank you very much for watching. See you in the next video. Bye-bye.